Kirchhoff's current law states that in a closed circuit, the sum of the currents leaving any part of the circuit is equal to the sum of the currents entering that part of the circuit.
To visually demonstrate the concept of Kirchhoff's current law, imagine that this 1/4 cup of water is actually a 1/4 cup of electrons. As we pour the water down this original path, the water is then split and goes in two different directions, just like electrons being split to become a parallel circuit. The amount of water is conserved, however, despite being split, just like the amount of electrons in a circuit. So here's the circuit we are working with. If Kirchhoff's current law is true, then the current going into the first node will be equal to the summation of the currents leaving that first node. Additionally, the summation of the currents going into the second node will be equal to the final current leaving that second node. Lastly, the current leaving the battery will be equal to the current returning to the battery.
So here I'm about to build the circuit. I have my breadboard, some wires, 3 1 kilo ohm resistors, a battery pack, which is about 4.7 volts, and my voltage meter. So, let me build the circuit. So, the voltmeter right now is reading the current leaving the battery and going to the first node. And this is the final current leaving the second node. So this is the current measurement of the current going through the branch with only 1 kilo ohm resistor. And this is the current going through the second branch.
So here's a digital version of the measurements we just gathered from the breadboard. The total amount of current leaving the battery is 7.05 milliamps. This is equal to the current returning to the battery, which is also 7.05 milliamps. As you can see, the current of 7.05 milliamps enters the first node and is then split, creating a current of 4.7 milliamps and 2.35 milliamps. The sum of these two numbers equals 7.05 milliamps. At the second node, the 2.35 milliamp and 4.7 milliamp current are combined to create the leaving current of 7.05 milliamps. The slight variation in measurements between the breadboard and the computer simulation can be attributed to error in the voltages or the resistance of the resistors.
Here we have a happy suburban home. In this home, the electric box supplies the power to everything in the house that uses electricity. We have a TV, a lamp, an alarm clock, and a toaster. All of these work because all of them receive the same amount of voltage, but different amounts of current based on how much electricity or power they use. Here's a simplified version of the circuit inside the house. Every element of the circuit has its own little loop, and within these loops, every loop has the same amount of voltage. So, no matter what you plug into every electric outlet, everything else and any other electric outlet can turn on also.
This circuit applies Kirchhoff's current law. All of the currents going into every element of the circuit, such as the toaster or the lamp, come back into the electric box at the end of the circuit. Thus, all of the currents leaving the electric box equal the currents coming in, and the net current flow is 0 at that point of the circuit.
With all this evidence, it is apparent that the Kirchhoff's current law holds true.